In this video, we're going to discuss differentials. Differentials are related to our linearization that we were discussing. So let y equal f of x be a differentiable function. The differential dx is an independent variable, and the differential dy is a dependent variable given by dy is equal to f prime of x dx. Now, what do all of these mean? We can see our picture here. We have some function f of x, and we use this tangent line to approximate this value here. So in this picture, we have dx, which is our differential, our independent variable, is equal to the actual change in x that we are dealing with. We have an actual change in y that we want to estimate, and we estimate this actual change in y by calculating this change in y on our linear equation, and that is our dy. So dy is the estimated change in y. Delta y is the actual change in y. And dx equal to delta x means that the differential dx, the actual change here, is the same as our estimated change in a sense. We are assuming we have this amount of change in x. So if that is the case, what is our estimated change in y with a given change in x? All right. So with this information, we can kind of see that this is related to the linearization because this dy just helps us get our change in y, or estimates our change in y. So let's use this to do a couple of examples. So here is our first example. Use differentials to estimate the square root of 100.5. All right, so this is our question. What do we do? Well, we need to first determine what the function is, and that is that f of x is equal to the square root of x. F prime of x is then 1 over 2x to the negative 1/2, which is, in other words, is 1 over 2 root x. So what is our dy? Our dy, our differential, is 1 over 2 root x dx, because again, dy is f prime of x dx. And when we want to calculate this when x is 100 and dx is equal to 0.5. Why did I choose when x is 100 here? Because we know the value of the square root of 100, so that'll make our calculations easier here. So let's go ahead and calculate dy now. This is 1 over 2 times root 100 times dx, which is 0.5. So this is 1 over 20 times 1 over 2, which is 1 over 40. So that's what our dy is. So the square root of 100.5 is approximately the square root of 100 plus dy, which is the change, our estimated change from 100 to 100.5 on this function. And what was that again? That was 1 over 40. So we get 10 plus 1 over 40, which is 10.025. And now if we compare this to the actual value of the square root of 100.5, this is approximately 10.02496. So we see that we can get pretty close with this differential, with this idea of linearization, or really in this case, we're using differentials. Okay, let's do one more example where we use differentials in this video. And this example is going to look like this. So we have the radius of a circular disc. Circular disc is given as 24 centimeters with a maximum error in measurement of 0.2 centimeters. So what this means is, suppose we have a circular disc and we have some kind of measurement tool, and we measure that the circular disc has a radius of 24 centimeters. Well, with any measurement tool, there's going to be some degree of error on that measurement tool. So let's suppose that we know that the maximum error we can have is 0.2 centimeters. Perhaps we're using a ruler, and there's tick marks every 0.2 centimeters. So we know roughly what the radius is, and we know by about how much we can be off. And that is 0.2 centimeters here. Okay, so what we're going to do is we're going to use this information, use differentials, to estimate the maximum error in the calculation of the disk, calculation of the area of the disk. So dy here is equal to f prime of x dx. Y is equal to pi x squared. So this tells us y prime is equal to 2 pi x. And what are we actually doing here, right? So this gives us our y prime, which gives us our dy equal to 2 pi x dx, which we can plug in our 24 centimeters times our 0.2 centimeters and get an estimated maximum error of 48 pi over 5, which is approximately 30 square centimeters. And now, again, what is this doing? Let's make sure we understand what we're doing there. We use differentials to estimate the maximum error. So if we know the error in the measurement of our radius, we can calculate the area by just doing pi x squared, where x is 24. But we want to know the error on that, the maximum error on that. Well, if we calculated some area here using this formula, but our radius could have been off by 0.2 centimeters, then the final area is going to be off by at most this estimated differential, this dy. That's its maximum change, possible change here. So this calculation here of dy gives us our maximum error in the area. So we have another related question here, B, which is what is the relative error and what is the percentage error? Well, our relative error means the error divided by the total amount. So essentially this gives us, again, a relative error. Or it gives us the percentage error when we convert this value to a percentage. So what percentage of the actual calculation is our error? And that's what we're calculating here. So our relative error is equal to the actual change in y over y which is, we can estimate by dy over y. Dy is our estimated error, our estimated change. And what is this calculation? Well, this calculation is 2 pi r dr, right? That was our dy. And y is actually just pi r squared. So we can cancel here, and we get that the relative error is 2 dr over r, which is equal to 2 times 0.2 over 24 when we plug in our actual values, which is approximately 0.4 over 24, which is the same as 1 over 60, which is 0.016 with the 6 repeating. And thus, the percentage error is 1.6 repeating percent. And that's it for this video.